In this video we are going to talk about how to practically construct some of the giant space habitats seen in science fiction, and considered at various points in the last century by scientists at NASA. We will cover how the same technology could be used in the very near future to build space stations at significantly lower cost and risk compared to anything else previously or currently proposed. But firstly, a potted history of rotating space stations. Konstantin Tsiolkovsky is credited with coming up with the idea in 1903, the basic concept being to create gravity in space through rotation. 25 years later, Hermann Potočnik extended the idea and suggested a 30-meter diameter torus-like structure. Roll forward roughly another quarter of a century and Wernher von Braun suggested a 76-meter diameter space station capable of holding up to 80 people. This was apparently taken reasonably seriously and briefly part of strategic thinking at the fledgling NASA, formed just a year earlier. In 1962, Kennedy had different ideas. Any work not focused on getting boots onto the moon was presumably completely shut down. A year after the first moon landing, Larry Niven took the concept of a rotating space habitat to something of an extreme, imagining them to be nearly 300 million kilometers in diameter, or the same as the orbit of the Earth around the Sun. A few years later, a NASA concept study came up with the Stanford Torus, 1.8 kilometers in diameter and designed for roughly 10,000 people. 4 years later, physicist Gerard O'Neill proposed an 8-kilometer diameter design, although cylindrical in shape. In 2001, the extremely successful entertainment franchise Halo imagined giant ring structures 10,000 and 30,000 kilometers in size. The idea was then floated again in 2019, with one notable detractor. That about covers a brief history of something that has yet to exist. The simpler design of a non-rotating space station was favored by the collaboration involved in the ISS, with the ability to do R&D in a weightless environment a key requirement. It was, and still is, difficult to imagine how a ring structure might be designed and constructed in a way that wouldn't be extremely complicated and cost-prohibitive. But what if that wasn't the case? And what about if you actually wanted the gravity? Weightlessness is, after all, an unhealthy long-term environment, with constant inherent challenges to completing the most mundane of tasks. Not all future missions will be focused on experimenting in zero-G. Having artificial gravity would be beneficial to both the crew's health and productivity. Let's illustrate the process by building von Braun's rotating habitat. Manufacturing starts with the assembly of a very thin seed ring, with an inside diameter the same size as that of the outside of the habitat being constructed. The ring sections lock together and can be positioned using a suitable drive mechanism. An articulated robotic arm ending in a 3D print head is fastened to the structure used to rotate the ring. Multiple print arms can be used in parallel. During manufacture, the seed ring is rotated constantly in one direction. For each full revolution of the seed ring, the print head is held in a fixed position just above the surface. It prints an extremely thin circular bead on the inside of the seed ring. The print head then moves a very small distance and the next revolution is printed, and so on. Additive manufacture inherently allows overhangs to be constructed, meaning that from a tiny seed ring a much larger shape can be grown. Internal structures can be created to accommodate basic services, and there is the potential to print with different materials. Structures and access holes can be created perpendicular to the direction of ring rotation by precisely stopping and starting the print during each rotation. Imagining better graphics, this is how the process would appear from the outside. And similar as a sectional view. There are potentially multiple different types of print head that could be used depending on the materials required, and 3D printing has been successfully tested on the International Space Station. There is no reason in principle why multiple different materials could not be printed simultaneously. Relativity Space is already printing large sections of their rockets on Earth using a quite similar approach. In the following video taken from their website, it is worth noting that the forklift is there just in case something goes horribly wrong, and this orange platform is certainly not integral to the additive manufacturing process. The printer arm appears to be articulated to allow for a wide range of movement, and there are tracks allowing the whole unit to move relative to the rotating backplate. Notice how little the print head actually moves on this very speeded up video. Here's a normal 3D printer for comparison. Notice how a relatively acute overhang can be produced. There are multiple advantages to this method of manufacture compared to traditional fabrication where subassemblies are manufactured on Earth and assembled in orbit. With only a small number of moving parts and only one machine required, the production facilities should be comparatively cheap when considered against other imagined construction methods. Infrequent small movements of the print head during the manufacturing process results in little inertia to overcome, meaning the equipment can be light duty and low cost. Less movement means there will be less wear on any bearing surfaces, something that will be important for a long print. The print process is automated, but manual involvement may be required to ensure the printer is constantly stocked with sufficient material. Fit out of the hatches and interior with all of the required equipment will likely be at least partially a manual process, but this can be started before the print has been completed. The manufacturing process is scalable, which has major advantages when thinking beyond any current design. The detailed measurements and learnings provide a solid analytical platform from which to scale up sizes and quantities. The raw material needed to build the main structure is likely to be higher density when packaged for launch than prefabricated structural elements requiring assembly in space. Potentially this might lead to less overall launches for the same final mass. This method of manufacturing allows you to build shapes that would not be easy or in some cases possible by any other means. And there are a host of benefits that all derive from simplicity. For every separate item that goes into space, here's a probably non-exhaustive list of what needs to happen first. Each of these activities has an associated cost. Less components means less cost. Short of catastrophic impact, it is difficult to see why an aluminium torus structure could not be used more or less indefinitely, and for multiple purposes, assuming suitable internal equipment upgrades. This makes the construction of such a facility for ongoing leasing purposes very commercially interesting. Since you only technically need to be one revolution forward in the design, there is plenty of scope for working on it whilst it is being printed, perhaps floor by floor. During the manufacturing process, it will be possible to get a highly accurate model of the actual surface in real time and potentially to inform the design of mating fitment parts fabricated on Earth. By building the internal services directly into the main infrastructure, there is lower failure risk either through design or in service. Less components means less interfaces means less failure points. Clearly there are many technical and engineering challenges and these potentially non-trivial questions to answer. What type of feedstock material and print method to use and how to stock the print head? How to ensure adhesion to the seed ring? How to prevent warping? What the impact of material cooling rates with no convection has on the ability to print and general thermal management across the system? How to continually rotate the habitat from a fixed point as it grows, it will tend to slow as material is added. How to stop it becoming unstable? How to rotate it in free space when it is complete. How to make linear movements in free space. In order to test the concept, this machine, originally intended for a different purpose, was converted into this machine designed to build miniature space stations, thus conclusively proving it is possible to imagine finishing the coding for printing a space station on the inside of a ring on a small scale on Earth. But what do the numbers say? Is it practical? A basic model was constructed to answer this question and is linked in this video. Data is added to the model to define the basic shape, material and manufacturing parameters for the torus. The 3 columns indicated allow comparison of different values. Values are calculated for space, material flow rate, duration and power. Starting with a habitat of the size proposed by von Braun, values are entered for the diameters of the torus and the wall thickness. A floor of the same thickness is assumed. Additional print swept area can be added to approximate more complex internal structures and the total print swept area calculated and later used to determine the number of revolutions required and total print time. Volumes and floor space are calculated. Various print parameters can be adjusted and the print time calculated. Material selection is used to calculate various production rates. Power requirements are calculated and converted into solar panel dimensions. The von Braun habitat looks entirely achievable. Based on the numbers from the model, it is possible to very roughly estimate when the technology might be available for each main part of the manufacturing system. The print head feels very much like an extension of current technology, although novel material stock and feed systems will probably be required. Including the necessary in-orbit prototyping, it should be possible to start manufacture in well under a decade. The technical challenges don't appear to be relatively difficult or in any way insurmountable. However much propulsion technology progresses to shorten journey times, there are still good reasons to want gravity on the support facilities required for future space exploration and exploitation. If the ultimate objective is to save humanity from extinction, this concept is a stepping stone to both Mars colonization and larger-scale off-world habitats. Much of the learnings derived from construction of the initial habitat could no doubt be applied to building something akin to the Stanford Ring. However, it is possible that new technology allowing the print head to freely float and position itself in space will be required for something this big. Raw materials would also be one of the main constraints. Moon rock would need to be mined, processed and shipped or fired to the print heads at a rate of 4,500 tons per day. Power requirement would be immense, needing a minimum of 2.5 square kilometers of panels or 1 gigawatt of power from other sources. It doesn't feel totally unrealistic to build a Stanford Ring well before the end of this century, should there be a desire to do so. The rings from Halo 5 are unfortunately quite a long way away and would probably require metals from asteroids to be mined and processed first, and then to build the moon rock mining and processing equipment and print heads. The gigantic power requirements would need to be supplied from some unknown technology. There is also the minor issue of shifting the moon's orbit, which might be considered a bad thing to do. If you can't afford to build your own rotating space habitat, treat yourself to a reversible conversion for your work van instead, and thanks for listening.